to pay. My head just feels in pain. I missed the bus and they'll be hell today. I'm late for work again, and even if I'm there, they'll all imply that I might not last the day. And then you call me, and it's not so bad, it's not so bad. I want to thank you for giving me the best day of my life. Oh, just to be with you is having the best day of my life.
I suppose the fundamental idea to the particle pictures approach is that substances need to be explicitly described in terms of their particles. But language is incredibly important when you are explaining invisible things to students, because the particles of sodium hydroxide and the particles of copper chloride and water and the particles of starch, the particles of aluminum, are essentially invisible. Particle pictures approach can take a number of different avenues. We can picture the particles this way when we use the words like copper 2 chloride or CuCl2. The important thing is we don't just merely say copper 2 chloride, we don't just merely say CuCl2. We explicitly show the particles. If we're talking about solid copper 2 chloride particles, we use pictures like this. If we're talking about solid water, we would use a picture like this, or liquid water, a picture like this. We can use, from a particle picture standpoint, these are a bunch of smaller fridge magnets. These particles are poker chips with magnets glued onto the end. To move the water particles around and show the breakup or dissolution of a solid, we can do so using, and we should do so, using particle pictures. Now we can talk about the copper 2 chloride solid being half dissolved. We can talk about individual copper 2 particles in water. That doesn't mean inside the individual water. In fact, it means among the water. We can represent a chemical reaction, saying one of these, two of these. There's a CO2, there's an H2O, and there's another H2O. What did we have here before? We had here before a CH4, and we had two O2s, and now we have one of these and two of these. We had one of these, we had two of those, we now have two of these, we have one of these. This is a container filled with water particles arranged like a liquid, or arranged in the liquid state. In and among this container of water particles are some copper +2 particles and some chloride particles. If we need to represent that, we do so with particles. This is a container of sodium hydroxide? No. Sodium hydroxide solution? No. This is a container of water particles, liquid water particles in the liquid arrangement, and in and among these liquid water particles, or the particles in the liquid arrangement, are Na+ particles and OH- particles. The key idea, again, is to make sure that when you're talking about substances, that you are explicitly referring to the particleness of the substances, and that when you talk about the particleness, you support that language with any number of an array of visual tools that are part and parcel of the particle pictures approach. The rest of the video is going to go into some detail with some of the specifics on each of these methods. I'll show you how to make some of these things. I'll show you how to do this some of the pitfalls and benefits and pros and cons to this particular method. I will show you some tricks with the handouts. And in addition, anything not in the video is because we don't have time to put it in the video. So we have support documentation. If you don't have any support documentation, if you only are looking at this video, then contact us at the address you see at the beginning or end of the movie. How many of you have had the question go through your head whether or not the particles sit right on top of each other or whether or not they tuck in tight? Just want to see a show of hands. Okay, that's over half the class. Excellent. Now what I'd like you to do is show liquid water.
Yeah.
Okay, and listen up please for the next bit. Please tell me you guys used to play the following game at home when you were a kid.
Oh, house.
And the game is... No, the game is... What? The game is... The carpet is lava.
Yeah, all the time. That's on you. All the time. That's how I broke my arm.
Really?
Yeah, I was trying to from coast to coast and I fell.
That's great. There's an ant playing that game and the ant is on top of the poker chips. Now that ant has to be able to go from any one chip. I want to see solid salt at the bottom of that beaker of water, and there is water around the side and on top of the solid salt.
But if that was the problem, how would it get
A good model almost begs questions to be asked of it. High-quality science education requires students to periodically create and pursue their own questions, so it should follow that students need to use models that promote good question-making. Our case studies show that students immersed in a particle picture approach create more intelligent questions of the science, ask those questions more frequently, and, likely as a result, are able to follow their own reasoning into additional and deeper research questions. Students almost always ask the very questions whose content the curriculum document wants us to cover anyway, so this approach leads students down all the prescribed paths. Students rarely ever phrase the questions elegantly, but they do ask key questions. What's the difference between molecular versus ionic dissolution? What is solubility? And explain the concepts of saturation and supersaturation. Initially, we do not obsess over science definitions and terms. The sensibility of science words inevitably emerges as we move from where students are at to where we want them to be. This clip shows students working in small groups learning how to balance chemical reactions.
OH2, 3 of them. Mg, OH, Mg, these are all OH, and a 2.
What happens when I mix 3 molecules of NgOH2 with 5 particles of HCl?
We need more blue chips.
Where's the CL? Here are the blue chips.
Some of them have CL, like, let's just try to use those ones. So we had 5 of those and 2 of those. One more, we need 1 more of these groups. Okay. So now we need to create H2Os and MgCl2s as we can to complete all the chips. 2 H's and an O of black. There's one. Okay, but let's try to do one of the big ones. MgCl2. Two of them. There we go. And do one of these. Oh yeah, do that. And then let's do another one of these. So H. Wait, we can't have them. We don't have MgL. No, you can have all 4 of them. You can have all 4 of them. Oh, there we go. We're done. We're done.
We got it. We got it.
1, 2, 3, 4, 5, 6, 7. Right? Yeah. Okay. Okay, let's start with everything, right? Yeah. 2 H's.
So Megs, you're saying you're liking this? How come?
Now I understand.
What do we have?
Maybe write down a note and I can see if I actually look at it, but then I wouldn't know if I actually did. Now that I'm doing it, most that I understand white and 2 blues. We can leave this guy. We can do that. This one.
We're done. We did it!
Okay, we're done. We're done.
How many H2Os? Done.
Begin with a KClO3. So you physically take the particles and you put them on the board where the spots go. And then you bring it down to make the KCl and then the 2 O's. But you still have an O left, so to balance it out, you have to draw another KClO3. So then you take the particles or the poker chips and you add them again. And then you're going to bring them down to make another KCl, another O2, and then you have 2 left, so you make 1 more. So then you begin with 2 KClO3 and you end with 3 O2s. And you finish with KCl2, or 2 KCl. and that's it, balanced it.
So you start with one KClO3 particle, and you want to get one KCl and one O2 particle. So you move these down here. So you get one KCl, but then you have 3 O's, so it's not balanced. So you have 1 O left. So in order to balance the picture, you have to get another one of these. So then you have 2 of those. So you get a K. Yeah. O. So then again, you move these down here, and you end up with 2 KCl's. And then you bring down your oxygens, which is oxygen, but anyways. And you have 3 oxygen.
So this is nice if you don't like the idea about the cost of whiteboards and you like kids being able to manipulate things. That's a nice way to do it as well. Give each of these kids, we have a class set of 10 of these. You're breaking up the NAs and the whatevers. Great.
Allows us to show students' work. We can debrief the correctness and incorrectness of answers, and we can discuss the acceptability of various variations of correct. We can debrief the correctness and incorrectness of answers, and we can discuss the acceptability of various variations of correct answers. In effect, we can provide on-the-fly rubrics, sample scoring, and large group feedback. Teachers can see which conceptions are taking root and which misconceptions need to be addressed.
Is there negative charge to the class? Okay. Yes, just great.
That's right.
Yeah.
Okay, and convince us why this drawing pictures and being able to talk and stuff is actually a good idea.
Because like once you draw it, you
Let's be honest, a lot of what happens in a classroom involves talk, so we should figure out how to talk particle pictures.
Sodium chloride particles stick to each other. Hydrogen chloride particles don't stick to each other. So you should have all your hydrogen chloride particles in and amongst the water particles. Put in H pluses and Cl minuses. No. The HCl is together, touching each other. That's an H plus, and we've got Cl minuses, and we also have Na pluses, and we also have OH minuses. Will these particles bump into these particles? Any takers? Yes, ma'am? What will happen? We don't use the word they. Says who?
They're H particles and Cl particles all swimming around in that is H particles and Cl particles. To the test tube of H particles and Cl particles, we're going to add, so if I take an example, this is magnesium. Whenever any of those particles are stuck to itself and only itself, so say I have come to the test tube that had H particles and Cl particles. What we're trying to figure out
Li plus, F minus. This stuff is called lithium fluoride. Minus, minus, minus. Minus Cl. Minus Cl. Minus Cl. Al plus 3. This stuff is called aluminum chloride.
The circles that we use to encapsulate the objects or particles allow us to show students precisely which object or objects we are referring to when we give our verbal and written descriptions. Without those pictures, students have no way of seeing what we're picturing in our heads when we talk.
Notice that there's not two leads, but this is lead 2. This stuff is called lead 2 iodide. The imprecise.
Don't use the word it and don't use the word they in your classroom. Sometimes when we say that salt is dissolving in water, we're actually talking about a bunch of them dissolving among a bunch of those waters. So just don't even use the words it and they at all, and instead require that your students and you explicitly talk about the particle or particles. Don't use it and they.
Without interrupting.
So our experiment We wanted to know what would happen if we adjusted the ratio of NaOH to pheno. So our observations were...
Time out. I want you to back up again. Remember, we don't talk about NaOH, we talk about NaOH particles.
Okay, let's do it.
Good.
What would happen if we adjusted the ratio of NaOH particles to pheno particles? Our results were a lot of pheno particles and 1 drop of NaOH particles. It was clear. A lot of NaOH particles and 1 drop of pheno, it tended like pheno particles, it tended like pink. An equal amount of NaOH and an equal amount of pheno, it was a magenta colour. A large amount of NaOH.
Time out. It was a magenta color?
Yeah, it turned magenta.
Okay, it's not, listen, it's not magenta, the particles.
Okay, the particles turned magenta. A large amount of NaOH particles and a medium amount of pheno particles, the particles turned purple/dark pink.
Excellent, thank you.
I know you CCR.
So what's that?
It's where we write down the formula and then we have to do the particle picture.
Okay, and you're working in teams, how come? Explain that.
So that we can together.
Yeah, 2 of them. And then that's
And I think SO4 is
a special one.
yeah.
Okay, and convince us why this drawing pictures and being able to talk and stuff is actually a good idea.
Because like once you draw it, you can actually see for yourself, you're just copying it and you're not really grasping it. And then just looking at this, then you can see that there's 4 of these, 2 of these, and then you can put it together yourself. Rather than just
Phosphate,
So we can't, it's not sulfate.
Bring a CR in the middle, obviously. We'll have a +3 charge. And sulfide is sulfide. Oh. And it'll be sulfur.
Sulfur is, it'll be a +2, 4, 6. So, oh, we have 2 CRs.
We'll have two CRs and a +6.
Yeah.
Okay, so S with a +6 or -6.
Yeah.
-6, and then CR -3 and CR -3.
But then that doesn't make it neutral.
It does.
No, we're gonna
Or,
get
yeah,
here.
this
These
should
have to be
positive.
positive.
Yeah, positive.
Okay.
And it'll be CR subscript 2S.
And S is our negative charge, so it's lost. Okay. Doesn't, yes, just great.
That's right. Yeah.
Okay.
Your face. No, cancel.
Just, do we have, no, we don't need that. Just when we're ready.
Nitride. Nitride is N, and there's only one. How many charges? 2, is it? Negative 3, or negative 1, negative 1, negative 3, and 3. For what? Okay. And with the formula? No, this is no, yes, it's positive though.
Nitrite, what is N stand for?
What am I doing? Yes. No. So it's
R3.
and what's the name?
Okay. And name, it's the formula.
Oh.
Here we good? Charge is 0?
This is negative 1.
It's negative 1.
No, wait. That looks like a positive. It does not.
Good.
Okay, good. Okay, go. We're all charged, yeah.
Yo, nitrite is
Point.
Follow.
Point.
Nitrite.
Point.
We're getting there.
Go, come back to it.
Right there.
Right there.
Point. Negative.
My first introduction to particle pictures was watching John do the introduction to nomenclature. And the thing that surprised me was how quickly the students could manipulate those elements to come up with a name, and the types of questions they were asking for an introduction to nomenclature unit. They hadn't had those tangible things in front of them. I think they wouldn't have had time to even process that type of questioning as they figure out what's going on. But by actually physically having a carbon particle and an oxygen particle that they could manipulate, that took away some of that sort of initial confusion, and then they could delve deeper into what kind of questions they need to get at in order to really understand the nomenclature. If one of the students wasn't understanding a concept or wasn't understanding a question, another student could draw out what they were seeing in their head to help get the other person to understand. So if someone was saying, I don't understand why this particular compound is being formed, someone else could either, if they were working with poker chips, say, well, you move this one here and this one here, and now you have this product. Or if they were working just on pieces of paper or on the whiteboards, they could draw out, well, first you do this and then you do this. And I think it made a lot more sense for students to see the particles and see them moving around rather than just writing out chemical formulas that in essence become letters that sometimes don't make sense to. For me to think, I'm going to be in front of a classroom where students might ask questions that I'm not only am I going to be confused about how to answer it, I might not even understand what they're asking. So with particle pictures, a lot of the times I found myself saying, well, tell me what I should draw on the board, or what do you want me to draw, or what would you draw, to help me understand where they were coming from. So when they were saying, for instance, I don't understand why the carbonate doesn't break apart, or why this thing doesn't break apart, I was understanding what it was. But then if they were drawing the carbon particle and the 3 oxygen particles, we could then talk about that whole particle as one. It just made a lot easier for me to understand what they were trying to get at, and for me to then explain to them what elements of that particular particle specifically we were dealing with.
And then also from the other kids sitting in the classroom, you just put the question visually on the board.
Yeah.
It's not in your head, and it's not in the student who asked the question's head. It's on the board. Right. Everybody can see.
So by drawing that, we're all on the same page, and there's no confusion there. There's no way you can misinterpret that picture.
How did you feel with the amount of work that was involved in just setting up this process? Because
I think it's time-consuming in the sense that, yes, you are drawing out all the particles on the board. I think the value, though, is that you could spend 30 seconds on 10 questions algebraically or in formula form, and the kids still wouldn't get it. Whereas if you spent 10 minutes doing that one question in particle picture form and drawing out all the particles, you're going to have a lot more students that are understanding what you're doing when you move on.
so that makes sense. So it's like an investment up front, and
Exactly.
then it pays off dividends in the end.
Oh yeah, exactly. That's how I would see it.
Someone who is fresh out of teachers college too, and maybe obviously hasn't been exposed to it, but I can see probably maybe intimidated. What would you tell them?
Right. I would say not to be intimidated, because I think it does the exact opposite. It makes things that are, I'd say, abstract, or maybe weren't as concrete when you were a student, that much more concrete. So when you have to draw out something, you have to put a lot more effort into thinking about what's actually happening in a step-by-step process. And it's going to make it a lot easier for the students to understand, but it's also going to be easier for you to follow your own logic as you're teaching. What is it that I've explained to the students? What have I missed, or what have I left out? It's very obvious when you're drawing the pictures if you've sort of gone over a step and not really touched on what you need to be touching on. So I would say use it.
So I was just saying, I taught grade 11 biology for 3 years, and the first couple of years we go through meiosis, which is, superficially not a very difficult task. Traditionally in the textbook, in a two-dimensional way, the stages of meiosis are laid out, typically with 4 chromosomes, and they go through each stage, identify what's happening. But it is superficial. It's not actually something that they go into and really dissect and understand it, and that's what I want my kids to do. So the last year I've been using plasticine models for them to construct at their lab stations, where I give them first of all a generic set of chromosomes that everyone's going to go through and just make for me each of the stages of meiosis. And it was just an eye-opener. it made me realize how much the students didn't understand. They didn't understand meiosis at all. So after we, established this task of going through and constructing the stages with plasticine, it gave me a lot of flexibility. I could see where they were missing information or misinterpreting, a stage of meiosis or not understanding misconceptions. It gave me a lot of options to vary, just number of chromosomes, what would happen with regards to changes. It was just a very good way to dissect something that otherwise wouldn't be dissected in that manner. It just gave them a greater, a deeper understanding. So valuable. And now they have a picture in their mind as opposed to just some series of events that is in 2 dimensions in a textbook. So I wouldn't go back. It was just convinced me, giving them that tangible material to work with was just so valuable, to give them something in their head that they could. I already saw it,
Right.
but to show it to them, I mean, you can speak in words and say something, but you have 5 students in front of you, and possibly all of them are going to have a different picture in their head. But here's the plasticine model. Here's what's happening. Everyone sees the same picture. It's great. So that. Suction. Well, there's no such thing as suction. And then we start talking about, air pressure, differences in air pressure. Well, what is air pressure? Talk about particles then. We get into the concentration of particles and how dense they are inside the plunger as opposed to outside the plunger. And, once they start drawing pictures of the particles outside the plunger and inside the plunger, they begin to realize the light goes off. Oh my God. You're so right. It's being pushed against the wall, Mr. Geddes. It's not suction. It's not getting pulled against the wall. It's getting pushed against the wall. So, an example of particles being used just to understand the concept of how air moves into your lungs. So it made a good transition into that.
So Sam, what would your, from the perspective of a grade 11, primarily, grade 11 biology teacher, what would you say to convince grade 9 and 10 teachers to adopt a more particle-y based?
From the biology perspective?
From the biology perspective.
I would totally ask them, because they do mitosis in grade 9. At least not next year, but they did mitosis in grade 9. Let's say I'm doing it from a grade 10 perspective then. So the mitosis goes to grade 10, they're doing systems. I would challenge them to ask their students to construct something tangible to explain mitosis. So construct a model. Let's see how much you really know. Explain it to me. Explain the process to me. Or explain it, better yet, you're one teacher in a group of 30 kids. Explain it to your neighbor. Okay? And then maybe pick a few students to explain the stages of mitosis. And just see how much your students really understand. And dimes to donuts, I bet you if you got 30% of your class understanding what's really happening in mitosis, you're lucky.
Yeah, but let's just qualify. A moment ago, you said you were talking about the tangibility.
Yeah.
And you even made reference to the image that students have in their head versus
Right.
the image you have. And then now you said challenge the kids to explain. But couldn't they explain without having the right images or ideas in the word? Or do you mean to say that challenge the kids to explain in something more overt than words? Or?
No, use a model. So here's a model. Explain to me what happens in mitosis. That's what I want. I don't want a memorized list of events that's happening at each stage. That means nothing to me.
Something other than words.
Yeah, something other than words. I want something tangible. Here's some chromosomes. Show me what's happening. And if they can do that, then they understand it. But if they can't do that and they're just memorizing a list of events that's happening, they don't know.
Interesting. Great.
How'd that go, honestly?
Well, it was, for me, teaching grade 4 or 5, it was really the first chemistry experience for my students. They had pretty much zero exposure to chemistry. So we started off with the very basics, which is sometimes the most difficult questions to ask, but my kids were so intrigued by it, like what is a particle? What does a particle look like? How does a particle move? And we started with those really simple questions that were very encapsulating for the kids, and we moved along to some more specific things about how chemicals react with each other, how particles react with each other, and we moved into showing physically how photosynthesis works. And as well as thinking a little bit outside of the box, and they did a great job in being and having a lot of fun with the particle pictures in my classroom. And they loved the actual physical manipulatives. They loved the poker chips, they loved the whiteboards, they had a great time drawing, and they had a lot of freedom in doing it because we didn't tell them that they were doing anything wrong. So the exploration of chemistry was a really positive first kind of interaction with it, and I think at the end they all came away learning not just one thing, but a whole bunch of things about how things work rather than what things are.
So it definitely addressed their higher level thinking skills.
It absolutely did. It absolutely did. And they were very keen on doing more after John left. And, they had a lot of questions. And obviously, when you're getting questions, they're thinking about it. They're not just hearing, and they're doing. So for us, it was a real positive interaction in terms of science and in terms of finding possible solutions.
So as far as the different abilities in your classroom, how was that addressed with the...
Finding possible solutions.
So as far as the different abilities in your classroom, how was that addressed with the pictures?
Well, again, the nice thing about using the particle pictures, especially when we started with it, was there was not necessarily any wrong answers. So from your level 1 student to your level 4 student, from your ESL IEP student to your enrichment student, they all had the opportunity to kind of be on the same playing field in terms of it was something new. They were finding out questions and they were finding possible answers, and they weren't necessarily finding right or wrong.
And how would you describe the teacher's role in that?
The teacher's role was more of a facilitator, and in getting the kids to have inquiry about the topic we were doing, and maybe to facilitate more of the whys rather than the whats. And in that regard, it was easy for classroom management because the kids were working in small groups together. They were self-directed, and John and myself could just kind of go around and kind of say, that could be, that might be, you're on the right track. And the kids pretty much were self-directed in their lesson.
So is it fair to say that by walking around and observing the group work, you could tell how easily the kids were grasping the concept?
Absolutely, because they were all using their whiteboards. They were all putting things on their whiteboards. They were showing them to their classmates. They were holding them up. They were showing them to myself and to John. And that alone was showing that they were on the right track and that they were getting something positively done in their groups.
So it was like an assessment on the spot.
It was. It was, yeah, it was.
You like the whiteboards.
I love the whiteboards.
You still have a set, right? You still use
And we use them. We use them. We use them in small groups. We use them, I use them with my classroom, and the kids really like them. They find that they're doing something with them.
Now, are you still using the 2 foot by 2 foot or the smaller ones, or?
The 2 foot by 2 foot. We only have the 2 foot by 2 foot.
St. Boniface Elementary in Scarborough now has a whole set of 2 foot by 2 foot whiteboards. They love them. So grade 7 and 8 teachers bought a whole bunch.
Excellent.
Yeah.
Visiting your class on a couple of occasions, I was able to take a small group of students aside and ask them, you know, how do you like particle pictures? What are you getting out of this? How is it different from other things you've learned or other ways that you've learned? And they had glowing, you know, recommendations of being able to move things around, being able to talk to each other, being able to explain when somebody in their group didn't understand. You know, someone could say, oh, well, this is how it works, or move this like this, and that's how it works. And the concepts that they were explaining to me, and the vocabulary that they were using, and it was obvious to me that they understood what they were talking about, and that these really, what I found when I studied it myself, really difficult concepts, they understood and were talking about them, the different elements in the periodic table, the charges that they have, the transition metals, and how they combine with, you know, that with other elements in the table, and how the charges change. And I was just astounded at how they could describe this to me. And they were so eager to show me. They were fighting over the whiteboard pens to draw the equations out. And then they explained the cabbage water experiment and how they determined you know, acids and bases and the reactions that went on there, and balancing equations. And it was just, I was just amazed that kids in grade 10 could have that level of understanding of chemistry and not be, I don't know, for lack of a better word, afraid of chemistry, because it can be very overwhelming, all of that new information. Just totally hooked. I was hooked on particle pictures after listening to those kids. In my own class, well, particle theory is part of the grade 7A curriculum, and I find that kids can, you know, give back to me what they've seen in their textbook or in videos that I've shown them, or they can describe it orally, they can draw pictures of it, they can dramatize particle theory. But when it comes to applying it, it's very difficult. I might have 1 or 2 kids who can apply their understanding of particle theory to the outcome of an experiment that we've done in class. It's very difficult for them. And when I saw this, the particle pictures, then at least they have something to manipulate, to hook onto, to name, to move around and try to understand what's actually happening in the experiment, instead of trying to attach it to some abstract theory. So I look forward to using this in my classroom so that the kids can get some more application experience with it, rather than just giving me back some facts.
Do you find that you can do particle picture work, can you use the manipulatives with the age group?
Oh, definitely. I find, like, I'm a big fan of group collaborative learning, because these kids need to move, they need to talk, they need to, you know, have something to do with their hands, because if I expect them to sit down and just copy notes, I find that difficult myself to do, so I like to provide that environment for the kids, and this is perfect for that. They have, you know, their groups are set up. They've got the particle pictures to move around and discuss. And also, I like the fact that if one student doesn't understand it, there's 2 or 3 others that can try to reword it for them so that they will understand it. And also the concepts that I've introduced and modeled, they put into their own words, and that's how, you know, I can see that they're making sense of it. If they can rename it or explain it in their own way, then I can see that it's starting to become more or less abstract for them and more concrete. So that's what I love. They've got a method of explaining something. As far as the group work / collaborative learning goes, you would definitely want your structure for moving into groups and how each group gets the materials and how things are distributed and collected. You definitely want that in place before you brought your particle pictures in, which you would generally tend to do in the first term anyhow. So once you've got that established and you've got your standard groups set up and your jobs in each group, this will run like clockwork. So you've got your materials manager that gets the chips, you've got your recorder that takes notes on what you're doing, you've got your timer who says, oh, we've only got 5 minutes left to work on this problem, we better hurry up. And then you've got your spokesperson who will describe to the rest of the class, you know, what their group found. So once that's in place, this wouldn't be any problem. It'd be easy. And the other thing that I forgot to mention that I love about this is the in-class assessment. So I'm not taking papers home to mark. I can walk around and I can see, okay, they understand, they're almost understanding, they don't understand. And if I need some concrete evidence of understanding, I can have them answer a question, and then I can look at that and have, you know, something on paper to see what their level of understanding is.
Yeah.
Because I don't need anything else to mark.
Let's go and read the video.
Just feels in pain. I missed the bus and they'll be hell today. I'm late for work again, and even if I'm there, they'll all imply that I might not last the day. And then you call me, and it's not so bad. It's not so bad. I want to thank you for giving me the best day of my life. Just to be with you is having the best day of my life.
We're going to try again, just keep rolling.
Yeah.
Hi, my name is John McGoy. I'm here to show you some things that you can make very cheaply in order to do the particle pictures approach cheaply and effectively in your classroom. First off, I'll show you the poker chips. And these are, if you get a zoom in on this, thanks Jason. These are just dollar store poker chips. You can label them if you want with masking tape. You can label, you can put marker right on them, or what I like to do is I actually buy these Avery labels right here, they're pre-made, and run these sheets through your laser printer, and then you can get, you can print out whatever you want right on there. And so you can renew or refresh or build whatever poker chips you want. So those are cheap. I think they're about $4 for 300 or so. Poker chips, let's see, I've got 3 of these, and I think I have another 3 just like them. And I think that ran me a total of about $15 from the dollar store. Another thing you can do with poker chips to show the particle pictures is we have separate containers here. Get yourself some cheap fridge magnet. You can cut that, or in fact you can even rip that off, that cheap fridge magnet. Take yourself a hot glue gun and put, you get a zoom in on that, and put pieces of fridge magnet on the back of your poker chips, and later on in the video you'll see these poker chips sticking right onto the blackboard. So we'll have, I'll have a teacher set of these poker chips that I can demonstrate with. This stuff is dirt cheap. Obviously your hot glue gun is dirt cheap as well. Another thing you'll see later on in the video is we take some index card and we cut index card out and we glue some fridge magnet to the back of the index cards. I find that works a lot better than the ticky-tack, but obviously you could use ticky-tack as well. Moving over here, a staple of our particle pictures approach are our whiteboards. Sure, if you want, you can spend the money and buy yourself fancy erasers, but there's usually plenty of cloth sitting around. You'll see how easily that all cleans up. And again, you'll see the whiteboards used in the rest of the video. Typically what I do, we'll have, I have some erasers that came stock with the markers. I have a big supply of markers. I normally carry about 5 or 6 more than I need because they're constantly dying. Later on in the video, or no, actually not in the video, on the hard copy, I'll give you a recipe for some liquid that you can use, some solvent that you can add to dry erase markers to rejuvenate them. So it's nice to have a handful of extras so you can keep kids well stocked and then rejuvenate these. The solvent will basically add 5 lifetimes to your dry erase markers, so you definitely want to get the recipe on that. Again, over here, fridge magnets. Later on in the video you'll see lots about what we do with fridge magnets. There's a couple of different things you can do with these. You can stick them on the blackboard, obviously, because they're fridge magnets. You can put your own numbers, or you can put your own lettering on it, or you can go back to the Avery marker, the pre-made Avery markers or labels, and you can run these through your laser printer, and that's how we got that particular look there with the H2O. Fridge magnets. Cheapest and easiest way I found to make these. There's your tools right there. You can buy this at Home Depot or any home store. That's galvanized pipe. I believe they call this, that's an 1 1/4 by 6 inch galvanized, it's a gas nipple. And what I took it down to the shop class and I grinded this so it's actually a knife edge. And I did it on the other side as well. You buy yourself a connector, and what that lets you do, just screw those 2 together, just screw those 2 together, and there we go. And what that does is it lets me hit with a mallet a surface that isn't going to cut into my mallet, and it lets me have 2 knife edges, 2 because if one dulls I want to be able to keep on working before I send it down to shop class to sharpen. Take yourself a large piece of fridge magnet. A piece of fridge magnet about this large is going to cost you about $6. You take your stamp and you just wham, 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 and you can take the magnets out that way. You can also use, instead of that connector, you can use, they call it a flange, and you can buy a flange, and that certainly, if you're concerned about safety, that gives you a larger surface area to hit on. And I've got an inch diameter, I've got an 1 1/4 diameter there, and this I think is a 3/4 inch diameter. That whole, this whole thing right here is going to run you about $20, and it'll last you forever. You can make a million fridge magnets out of that. You can hammer them out yourself, or you can get a student to hammer them out. So all of these fridge magnets here I think that's $5 worth or $7 worth of fridge magnets worth of particle pictures, and again you'll see these things used in the video. Another option you can do, another option with the fridge magnets are these things we call, or I call Portaboards. It's a iron-based paint, and the nice thing is the particles or the fridge magnets can stick directly to that. So you can use these as small versions of whiteboards. Students can move their particles around on this, and they can hold it up and show the teacher. So we also have, I made a class set of those, and the nice thing is you can see you can store them with the magnets already stuck on them. A class set at 10 of these ran us, I think, $4. We bought the masonite in the off-cut bin, and the paint runs you, I think, about $20. So it's going to cost you $30 for a class set of these particular boards. Other than that, am I missing anything?
I don't think so.
You
I
don't
think
think so?
well, we've covered everything you brought in here with you. So
This is how we store all of our particles, our poker chips and the like. A bunch of these things from the dollar store. And they store things fine. We've got a box for our whiteboard markers. Make sure you read the instructions. I tell you how to fill these things up and recharge them. There's some chips. And there's a stack of whiteboards. And lastly, I've got a box with all of our fridge magnets. And we've got our fridge magnets here. And we have a class set of these Portaboards on this, and they can hold it up and show the teacher. So we also have, I made a class set of those. And the nice thing is you can see you can store them with the magnets already stuck on them. A class set at 10 of these ran us, I think, $4. We bought the masonite in the off-cut bin, and the paint runs you, I think, about $20. So it's going to cost you $30 for a class set of these particular boards. Other than that, am I missing anything?
I don't think so.
You
I
don't
think
think so?
well, we've covered everything you brought in here with you. So